Have you ever pondered the perplexing nature of light? Is it a particle, a wave, or perhaps both? This is a question that has puzzled scientists for centuries. The answer lies in the strange and counterintuitive world of quantum mechanics, where light can indeed be both a particle and a wave. This is known as wave-particle duality, a key principle of quantum physics. To understand this, let's delve into one of the most famous experiments in quantum physics, the double-slit experiment. Imagine a wall with two slits, and behind it, another wall where we can record the light. If we shine a beam of light at the first wall, it passes through the slits and hits the second wall. Now, if light behaves solely like particles, tiny, discrete units, we would expect the light to hit the second wall in two spots directly opposite the slits, like bullets shot through a wall. But that's not what happens. Instead, we see an interference pattern, a series of light and dark stripes. This suggests that light behaves like waves, spreading out and interfering with each other to create this pattern. But here's where things get really weird. If we try to observe which slit the light goes through, the interference pattern disappears. Instead, we see light hitting the second wall in two spots directly opposite the slits, as if they were particles after all. This strange behavior is known as the observer effect, where the act of observing changes the outcome of the experiment. So, we're left with a paradox. Light behaves as both a particle and a wave. But what happens when we apply this paradox to the cosmos? Stay tuned as we venture deeper into the mysteries of light and its journey across the universe. Enter the James Webb Space Telescope, our newest eye into the universe. The JWST, named after a former NASA administrator, is an ultra-sophisticated marvel of modern science. Its intricate design and advanced technology represent the culmination of over 2 decades of scientific innovation and engineering prowess. The JWST is equipped to observe the universe in a way that's never been possible before. With a primary mirror 3 times the size of its predecessor, the Hubble Space Telescope, it can collect significantly more light, allowing us to peer deeper and further into the cosmos. Its instruments are finely tuned to detect infrared light, which is crucial for observing distant phenomena. You see, the universe is constantly expanding. As it does, the light from remote celestial bodies gets stretched, shifting it into longer infrared wavelengths. This is known as redshift, and it's how we're able to observe the universe's distant past. The JWST's infrared capabilities make it an unparalleled tool for probing these cosmic depths. But the JWST isn't just about looking far, it's also about looking back. Its mission is to observe the earliest galaxies that formed in the universe, a period known as the Dark Ages. This was a time when the universe was opaque, filled with neutral hydrogen gas that absorbed light. It was only with the formation of the first stars and galaxies that the universe became transparent, its light finally free to travel through space. The JWST aims to capture this light, offering us a glimpse into a time before our current understanding of cosmology. It's like a time machine, bringing the distant past into the present. By studying these early galaxies, we can gain insight into how galaxies formed and evolved, and perhaps even uncover clues about the nature of dark matter and dark energy. But here's the catch. Could our understanding of light influence what we see through the JWST? After all, our perception of the universe is based on the light that reaches us. But what if the paradoxes of light challenge this perception? What if the universe we observe is not a fixed entity, but a complex interplay of light and matter? These are the questions that the James Webb Space Telescope may help us answer. Let's consider the journey of light from these distant objects to our telescope. Imagine, if you will, a photon of light. Born in the fiery heart of a distant star, it embarks on an unimaginable journey across the universe. It travels at a speed that humbles even our wildest dreams, a whopping 186,000 miles every second. And yet, even at this breakneck pace, the scale of the cosmos is so vast that it takes years, decades, centuries, and even millennia for the photon to reach us. Now let's take a step further into this cosmic dance. The light we perceive from distant stars and galaxies isn't a live feed. It's a cosmic replay, a glimpse into the past. Every time we look up at the night sky, we're not just stargazing, we're time traveling. That's right. The light from a star that's a billion light years away is showing us the star as it was a billion years ago. The universe is a grand stage, and light, the ultimate time traveler. It carries with it the tales of cosmic events that occurred eons ago. The birth of stars, the collision of galaxies, the formation of black holes, all these cosmic dramas are narrated to us through the light that reaches our telescopes. However, here comes the twist in the tale. The light we perceive is not as straightforward as it seems. It has a dual nature, sometimes behaving like a particle, other times like a wave. This paradoxical behavior of light, famously demonstrated in the double-slit experiment, raises some intriguing questions. So when we observe these distant stars and galaxies, are we seeing them as they truly were? Or is our observation influenced by the dual nature of light, its ability to be both a particle and a wave at the same time? This brings us back to our paradox. How does light's dual nature affect what we see? Remember our double-slit experiment? Now let's apply it to our cosmic observatory. The fascinating paradox of light we explored earlier challenges our understanding of the cosmos. If we consider light as particles or photons traveling through space, our observations of the universe become snapshots of the past. The light we perceive from distant stars and galaxies left those celestial bodies millions, even billions of years ago. In other words, when we gaze into the night sky, we are essentially looking back in time. However, if we embrace the wave nature of light, as suggested by the double-slit experiment, things become a bit more complex. Light waves, unlike particles, can interfere with each other. They can combine and cancel each other out, creating an intricate dance of peaks and troughs, bright spots and dark. This interference could potentially alter the information that light carries from distant cosmic bodies to our telescopes, subtly warping our perception of the universe. Consider the James Webb Space Telescope, destined to observe the universe in unprecedented detail. If light waves from distant galaxies interfere with each other during their long journey to the telescope, the images we capture might not represent the universe as it was when the light left its source. Instead, they could be a complex tapestry woven by the interference of countless light waves over cosmic timescales. Could this mean that our observations of the cosmos are not merely snapshots of the past, but also intricate patterns created by the wave nature of light? Could the universe we see be not just a historical record, but a living, changing entity, constantly altered by the journey of light? So are we seeing the universe as it is or as it was? The answer might just lie in the paradox of light. So, what does this mean for our observation of the universe's dark ages with the JWST? Well, the paradox of light could have profound implications for our understanding of the universe's early history. For one, it challenges the conventional wisdom that what we're observing are the fixed remnants of the Big Bang. Instead, it suggests that we might be observing parts of the universe that are currently situated at the distance of the universe's dark ages. Let's break that down. When we look into the depths of space, it's not so much that we're looking back in time, but rather we're seeing parts of the universe as they are now. The light from these parts, however, has taken some time to reach us. It's like sunlight. It takes roughly 8 minutes to reach our eyes, but that doesn't mean we're seeing the sun as it was 8 minutes ago. We're seeing the sun as it is right now. Similarly, light from the universe's dark ages that is just reaching us now doesn't mean we're seeing the universe as it was then. We're seeing the dark ages of the universe as they exist currently. But here's the twist. According to the light paradox, light doesn't travel in the way we traditionally perceive it to. Instead, it exists in a superposition of states until it's observed. This means that the light we're observing from the dark ages might not be from the fixed remnants of the Big Bang that have remained in place, emitting light. Instead, it's possible that we're observing light from parts of the universe that are currently situated at the distance of the dark ages. These parts might be vastly different from what we expect, challenging our understanding of the early universe and adding a new layer of complexity to our studies. This concept is mind-bending to say the least, but it's also incredibly exciting. It suggests that there's a whole lot more to discover about our universe and its history. It urges us to rethink our assumptions and to approach our observations with a fresh perspective. The paradox of light challenges our understanding of the universe and opens up new avenues for discovery. So next time you look up at the stars, remember, There's more to light than meets the eye. The universe is a vast, complex place, and our understanding of it is constantly evolving. Today, we've delved into the paradox of light, a phenomenon that challenges our conventional wisdom and reshapes our comprehension of the cosmos. We've explored the role of the James Webb Space Telescope, a marvel of modern technology that extends our viewing range into the universe's farthest reaches. However, with regards to the dark ages of the universe, it's important to clarify that what we are observing are not the remnants of the original Big Bang. Instead, we are seeing objects that are currently at the same distance as those dark ages. The light from these objects takes a considerable amount of time to travel to our telescope, and it's light's journey that we are witnessing. This understanding adds a new layer to our perception of space and time, prompting us to reassess our views about the universe. As we continue to explore the cosmos with tools like the JWST, who knows what fascinating paradoxes and mysteries we'll uncover next?